Washington, Tacoma. So hello, Martine. Thank you so much for joining us today. And we've run a little over, but we'll extend your time to give you the full case study time. And that will include questions and answers. So again, we encourage everybody to write questions into the chat and we'll collect those and ask them at the end. So with that, Martine, please go ahead and take over for us.
Thank you. Can you see my screen?
I can see the screen and hear you.
You hear me? Yes, okay. Thank you for the introduction. Thank you also for inviting me to talk here about my work. So my name is Martine De Cock. I'm a professor at the School of Engineering and Technology at the University of Washington, Tacoma. I have been doing research in the general area of intelligent systems for over 20 years now. And in the last 5 years, I have done work very specifically at the intersection of machine learning, privacy, and security. And today I will talk about some of our work on privacy preserving machine learning, and I will talk about the importance of cloud computing to evaluate the feasibility, the scalability of the solutions that we developed. Before I get started, I would like to give credit to my students and collaborators from the Privacy Preserving Machine Learning Research Group at UW-Tacoma, and in particular, my colleague, Professor Anderson Nascimento, who I run this group together with. The picture that you see on the left is a picture that was taken in December 2019 at the NeurIPS 2019 conference, and it was the last group picture that we took as a group, because it was right before the pandemic hit. So the students that you see, the individual pictures on the right, are students who joined the group more recently, and they have never actually been able to be in a group picture because all of our research meetings over the past year and a half now have all been remote. So they have done all their work remote, but they have contributed also substantially to what I will be presenting. So I want to give credit to everybody on this slide. So machine learning has grown really big as an area in computer science. And we have in this conference already heard about a variety of machine learning applications, and there are many more. For instance, when you apply for a loan or a credit card, really when you put in your application, you put your hands or your fate rather in the hands of a machine learning model that will decide whether your application should be approved or not. Or whether you are, or when you are online and you see some advertisements or some products being recommended to you, you see those because it's a machine learning system that decided that those should be shown to you, right? Or when you talk to a virtual assistant like Alexa or Siri and he actually understand you, that's machine learning at work. So whether, you know, people, whether you are aware of it or not, we all enjoy the benefits of machine learning many times every day. Okay, now, a challenge is that to work well, these machine learning systems consume a lot of data. And a lot of that data is personal data from individuals. And people are becoming increasingly aware of this, that you know, companies are collecting their data and using their data, and we are becoming more and more uncomfortable with this. You probably all heard stories or saw reports in the news about data breaches and scandals. You may recall seeing some reports about CEOs of big tech companies going to Congress, being requested there to clarify the data policies of their companies. And this growing acknowledgement of the need to protect the privacy of individuals has also already resulted in new laws and regulations. For instance, in the US, for many years now, we have had the HIPAA law that protects patient data, so healthcare data. And then more recently, 3 years ago in 2018 in Europe, the GDPR came into effect, the General Data Protection Regulation, and then at the same time in the US also, the California Consumer Privacy Act. And these are all laws that restrict what can be done with the data from individuals. So this actually creates a tension because on one hand, we have all these beautiful machine learning applications that use data. But on the other hand, we also now have these laws that restrict what can be done with data. And even if we hadn't these laws, if we wouldn't have these laws, then people may still be uncomfortable, to give companies access to their data. And even companies themselves may not necessarily want all this unrestricted access to data, because it can create liabilities for them, or it can put them, in a negative spotlight, create some negative publicity. So what companies also are looking for are solutions that let them keep offering their services that rely on data without necessarily having access to all the data in an unrestricted manner. Okay. So that brings me to the core question of my research, which is how can we, on one hand, protect the privacy of individuals, while on the other hand, do machine learning with private data? And I'm not the only one asking that question and looking for answers. There is a growing area of research called privacy preserving machine learning, where researchers are trying to address this issue with all kinds of different techniques, the so-called privacy enhancing technologies, the PETs. And I've listed the most important ones here, the most prominent ones here on the slide now. All these techniques can be used together. They are complementary in a way. And they also each come with their own trade-offs in terms of accuracy, privacy, and efficiency. Accuracy relates to how accurate the models are, the machine learning models are, that we can build while protecting privacy, because often protecting privacy comes at the cost of accuracy. So depending on the PET that you choose, you may have some loss of accuracy. Privacy means how well does this PET that I'm using protect privacy? Okay, some were better than others. And then efficiency means how fast can the machine learning models be trained when I'm also wanting to protect privacy. So you have these three different characteristics that are kind of fighting with each other in the different PETs. Okay, now the privacy enhancing technology that I use in my research is based on cryptography. So that's what I will be talking about next. When you think about cryptography, cryptography already goes back a very, very long time. Originally, encryption has been used for data in transit. So person A wants to send a message to person B. For this, person A encrypts their message, sends it over, person B will decrypt it. Yeah. And so the encryption is intended so that if somebody would come in and intercept a message, that person, that adversary, would not be able to figure out what the true message was. All they see is some garbled information. Yeah. So that is traditional encryption used to protect data while it is in transit. Then, with the arrival of modern computers, portable storage devices, it also became important to protect data in storage. So, for instance, encrypted hard drives, that's a very nice example of that. Those are forms of traditional encryption to protect data while it is in transit, while it's being sent, and to protect data at rest when it's stored. Now, what we need for privacy preserving machine learning in terms of cryptography is actually an entirely different animal. Why? Because we want to be able to train machine learning models on data while the data is encrypted. So what we need are techniques to do computations over encrypted data. So it's like computing with data that you are not allowed to see in an unencrypted manner. And for this, we use techniques from secure multiparty computation. Secure multiparty computation is an umbrella term for techniques in cryptography that allow multiple parties to perform computations together over their own private inputs without any of the other parties learning an input that doesn't belong to them. Yeah? Secure multiparty computation was originally introduced by Andrew Yao in the 1980s, but it's only recently, like in the last decade or so, that it has evolved enough to become scalable and usable in practice. I fully realize that this conference is about cloud computing and not about cryptography or secure multi-party computation. But if by any chance, by listening to my talk, you become intrigued and you want to know more about secure multi-party computation, then I can recommend this paper at the bottom here, written by Lindell, that was published last year in Communications of the ACM. It's a very nice introduction to secure multi-party computation. Okay, so why do we work with secure multi-party computation? What is so fantastic about it? What is so great? Well, it's great in terms of accuracy because it allows us to train machine learning models and use machine learning models with the same accuracy as you would have in the clear without using any encryption. So that's great. Then in terms of privacy, we can mathematically prove that there is no data leakage. So we can mathematically prove, give mathematical guarantees that if you protect your privacy preserving machine learning or your machine learning pipeline with secure multi-party computation, then the company will not learn anything about your data. So those are great to have. Now, of course, there's no free lunch in machine learning or in privacy preserving machine learning. And the catch is that doing computations over encrypted data is computationally demanding. There is a computation cost and there is also a communication cost, which in practice means that runtimes are going to become a lot longer than if you don't use any encryption at all. Yeah, so that's the efficiency component. Now, a lot of our research is how to develop MPC, so secure multi-party computation protocols that are efficient enough to use in practice. And that's where a lot of the intellectual fun in the research comes in. Yeah? And this is also where cloud computing comes in, and like why it's important for us to use the cloud in this research. Because to prove that our solutions work in practice, like you need to you can do some theoretical complexity analysis about the runtime, right? But we also always end up doing a lot of runtime experiments. And using the cloud allows us to do these experiments in a consistent manner on the same kind of hardware. Often we have several students working together on the same project, and now that we can do our experiments in the cloud, the students all have a place where they can go to use the exact same hardware, and we can do an apples-to-apples comparison. Also, we regularly have situations where we come up with a solution which we claim is faster than something that was published by someone else last year. And then to do a comparison, we can just look up what the hardware was that they did their experiments on and replicate that hardware by choosing something very similar in the cloud, like in terms of bandwidth, memory and whatnot, so that again, we can do an apples-to-apples comparison. Okay. Let me tell you a little bit more about how this machine learning based on secure multi-party computation works. So in supervised machine learning, you have two stages. You have the stage where you train a model, where a model is trained, typically on a large set of data. And then you have, for instance, a classifier or a regression model. And then you have the deployment phase, where you use that trained model to make inferences or predictions for new instances. Yeah? So that's the inference phase, or if you're doing classification, that would be the classification stage. Now, in both stages, you may want to protect privacy. For instance, in the training phase, it can be that you have data from different hospitals and say that these different hospitals want to actually work together using their data to train a more accurate model for disease diagnosis. So typically, in machine learning, the more data you have, the better, and the more accurate models you can train. So these hospitals want to pool their data together in some way to train a more accurate model for disease diagnosis. But the hospitals are not allowed to just give the data to each other because of HIPAA regulation. Yeah? So that's a use case for privacy preserving training of machine learning models. And then for inference, you may also want to protect privacy, because now you may have a patient wanting to use the trained model, but the patient doesn't just want to give their data to the hospital, right, or to the organization who has the model. And the model owner, on their hand, also may not just want to give their model to the individual, to the patient, because that model may be proprietary. And also trained machine learning models actually memorize information about the training data. So if you were to disclose a trained machine learning model, that may leak information, sensitive information about training data, which of course is also not something we want. Yeah. Now, we have done work both on privacy preserving training of machine learning models, so stage 1, and privacy preserving inference, so stage 2. In the interest of time today, I will talk a bit more about the inference phase, the classification phase, because that is the easiest to explain. And I will highlight more about how we use cloud computing in this research. So at a high level, you can think of doing inference with a trained machine learning model as function evaluation. And I will give a simplified example about spam detection in emails. So say that you have a user who sends an email. At some point, before that email reaches the intended recipient, that email will be pushed through a spam detection system. Yeah? For this, the email is first represented as a list of numbers, one way or another. Yeah? So the email, you can think of X, a vector of numbers. And the machine learning model, the spam detector, you can think of as a mathematical function. So you have this machine learning model that's owned by a company, and it's a mathematical function f. The exact shape for my explanation doesn't really matter. Okay. Now, what does the spam detection system do? It will evaluate that function f in x, and then compare it to a threshold, say 0.5, and if the threshold is met, then it will raise a flag. The system will say, hey, this looks suspicious, this email might be spam. Okay. Now, what is the tricky part? What is the challenge? That evaluating f of x depends on x, which is information coming from the user, and depends on information on this f, which is information coming from the company. And the user doesn't want to show X to anybody in an unencrypted way, and the company doesn't want to show F to anybody in an unencrypted way. So what is the challenge? Given X and F in encrypted form, compute F of X. So to do this, with secure multi-party computation, we let both the user and the company send encrypted shares of their information to servers. Yeah. So what you see here is an illustration of a secure multi-party computation scheme called additive secret sharing. And in this scheme, each of the participants rewrites all their information as the sum of numbers modulo some integer. So for instance, if the user has some number 9 representing something about her email, she rewrites that as the sum of 3 numbers modulo 17. 17 here is an integer that's chosen. It's like a parameter that you choose. Okay. So 4 plus 12 plus 10 is 26, which modulo 17 is 9 again. Yeah. And then the user sends each number to a different party. And you can think of these parties as virtual machines in Azure. Yeah. So the first one will receive number 4. The second one will receive number 12. The third one will receive number 10. Yeah. And you can easily see that none of these servers, none of these VMs by themselves know that the user's original value was 9. It's only if these 3 servers would collude and would put all their shares together that they would be able to construct number 9. Yeah. So in the same way, the user secret shares all the numbers that represent her email with the 3 servers in the cloud. And in the same way, the company secret shares all his trained model parameters with those parties or servers. Yeah? And then the servers start running an MPC protocol where they do computations over the encrypted shares. So they do computations over these secret shares. Now, doing addition of two secret shared numbers is easy. Those servers will be able to do that by just doing additions of their own local shares. Multiplication is more complicated. There are techniques to do multiplication of secret shared numbers, but that will involve some communication between the servers. But what they are sending to each other is encrypted information. But the communication aspect is important here because that will increase the runtime. Yeah? And all other operations that need to be done are done by breaking them down to the very basic level of doing additions and multiplications. So that's in a nutshell how you can do function evaluation based on secure multi-party computation. Now, what are the challenges? First of all, correctness. We need to make sure that the servers compute f of x and not something else. Huh? Second, privacy. We need to make sure that throughout this process, the servers don't learn anything about the original value of x. They don't learn anything about the model parameters in f, and they also shouldn't learn f of x. Yeah? So the servers learn nothing. And then the third thing, very important, efficiency, because we want this whole process to be fast so that it can actually be used in practice. Now, for efficiency, it's very interesting to study what kind of efficiencies you can have by playing around with different server configurations in the cloud. And what I mean by that is changing the number of servers. Here in this picture, you see that the information is secret shared with 3 servers, but you can also share with only 2 servers, or you can share with 4 servers, or even more if you would want to. And of course, when you have more servers, you have some more compute power, but you will also need to do more communications between the servers, which is not such a good thing because that will increase the runtime. But the most important thing is that when you have a different number of servers, you can start using different secret sharing schemes. So here I gave you an illustration of additive secret sharing, but there are different techniques in which you can secret share information like this. And when you have 3 servers, you can share in different ways than what would be possible if you only have 2 servers and so on. Yeah. So playing around with this is very interesting to get some efficiency gains. Now, an important question is, of course, whether all of this works in practice. Yeah. And so to show you that, I have an example here of a project that we completed this year. And in this project, we developed a secure multi-party computation protocol for privacy-preserving text classification with convolutional neural networks. So this protocol would allow, for instance, a company to detect whether the email of a user contains spam without the user needing to show their email in an unencrypted manner to the company. Okay. And to show that our solution is fast enough to use in practice, we trained a convolutional neural network for text classification, and we implemented our secure multi-party computation protocol Encrypted. Encrypted is Facebook's library for secure multi-party computation, and that's built on top of PyTorch. Yeah? And then we deployed it on Azure, and we managed to privately classify a text of around 600 words in less than 1 second. And the important thing to note here is that there is no accuracy loss compared to doing this in the clear, meaning without encryption. Yeah. One of the biggest practical challenges we had in completing this project was actually figuring out how to deploy Krypton on Azure. And the reason is simply, I think, because Krypton is very new and there is not much documentation available. So now we have figured out how to do it. So if anybody is, interested in doing something similar, feel free to reach out to me and I can share what we learned. Okay. And then another project that we successfully completed this year is for privacy preserving video classification. We studied a use case for automatically detecting emotions in video. So you see the video or the system, or there is a video rather of a user, and the system needs to detect whether this person looks happy or disgusted or angry or some other emotion. Yeah. So something like this is important for the development of empathy AI-based systems, like this is something that, like, there is a growing interest in the development of systems like that. But of course, users would be uncomfortable to use those if they have to give the system or a company free access to their raw video footage, right? So the challenge is how to do this in a privacy preserving manner. Now, to do this, so to do privacy preserving video classification, we have developed secure multi-party computation protocols for selecting frames, so selecting images from videos in a privacy preserving manner, and then classifying those images with a convolutional neural network, so kind of similar to the work on text classification, and then securely aggregating the inferred labels across the different frames, across the different images. And we have implemented those protocols in MP-Speeds, which is an open source library for secure multi-party computation. And again, we have deployed this on Azure. And so we use this with a convolutional neural network with around 1.5 million parameters, so to do the image classification. And depending on the security setting and on the number of servers we used, you can see here that we managed to classify a video of 5 seconds in under 9 seconds. That's not fast enough to claim that we can do video classification in real time, but hey, we were the first to develop a secure multi-party computation protocol for video classification, and we are very excited to see that it can work, right? So it's an important, very important first step in this direction. Okay. Yeah, and then this is an overview of some other work that we have done, both on privacy preserving training of machine learning models and on privacy preserving inference with the trained machine learning models. I won't go into details about all of these, but if you are interested, you can find these papers on my faculty webpage. And yeah, with that, if there's like anything I really would like you to remember from this talk, is that it is possible to do machine learning in a fully privacy preserving manner, using cryptography without loss of accuracy, but the main challenge is how to do it efficiently. And that is like a rich research problem area. And that's also why, as I mentioned before, cloud computing is important for us to demonstrate that indeed our solutions are scalable. This is something like using the cloud allows us to very easily and in a flexible manner choose the hardware on which we run our experiments. And it's great that we can like change the hardware settings from one experiment to the next, or on a daily basis or a weekly basis, which is something that is not possible to do with the hardware that is available at the university campus. If I would want to make the same kind of switches and every time like ask my department to buy a different kind of hardware and to install a different kind of hardware, I think that they will pretty soon ask me if I'm a little bit crazy and if I can please make up my mind. So really the beauty in using cloud computing for our research is that we have a lot of flexibility to choose what hardware to use from one day to the next, from one experiment to the next. Okay. And with that, I would like to thank Microsoft and the UW Azure Cloud Computing Credits for Research program for the donation of the cloud computing credits that made our research possible. And I would like to thank all of you for listening to my talk. Thank you.
Thank you so much, Martine. That's So I just love this topic because it's the kind of thing that just seems like it literally shouldn't be possible, and then like your work is just showing that it is, and that's wild to me. It's really cool stuff. So we have a few questions that we've collected. Let's see. The first one is, could you speak to how privacy-preserving machine learning might be used to help analyze data that's protected by strict privacy or confidential laws and certifications, like in healthcare settings for stuff covered by HIPAA or things like FedRAMP, without having to secure the cloud resources themselves?
So the technologies based on cryptography are not tied to any specific kind of hardware, right? So it's not hardware related or hardware restricted. So you could, in principle, use this no matter what kind of hardware you have available. I'm not sure if that is what the intent of the question was.
Yeah, I think that the heart of the question was asking maybe like, oftentimes when dealing with this sensitive data, using cloud resources can be difficult because a lot of them just aren't traditionally certified, you know, like to be used under this. So like, can you use this sort of technique to not have to worry about the cloud resources you're using because all of your data is encrypted before it gets sent to the cloud? Does this, is it compatible with those legal frameworks?
Yes, thank you, Naomi. That's yes, it is. Yes. So actually, initially when I started using the cloud, I think 7 years ago, it was because I was working with healthcare data. I was not doing privacy preserving machine learning at that point. I was working with healthcare data, and I ran into this issue that we had data sets that were, needed to be protected, and I had students wanting to do data science on these data sets. And then I started using AWS because the University of Washington had some agreement back then with Amazon that made it possible to set up a HIPAA compliant environment, right? And then I realized how difficult it is to do data science on data that needs to be protected, to this extent. And that is actually one of the things that triggered me to start working on privacy preserving machine learning. So with the secure multi-party computation techniques that I talked about today, you can do analysis over data where the original data does not have to leave the premises in a non-encrypted manner. So as you phrased it very nicely, so that's exactly it. Yeah, of course, that needs to be tied in with the regulations because, you don't want to violate any laws, right? So it's like you have this whole legal machinery that you also need to respect. Yeah.
Oh, it's exciting. I can think of offhand at least a few different groups that I'm working with that would really benefit from this kind of technique. And I guess to that point, we have another question. If a researcher wanted to consider PPML in their work, what would their first steps be to assess if it's applicable to the work they are doing? And if so, how would they get started using it?
Ooh, that's a good question. So anytime you're working with data and there is a need to protect privacy, right? When you do some data science, machine learning, and there's a need to protect privacy, PPML is applicable. But then you need to figure out what path would be best to meet your needs. There are simpler techniques that are not so computationally demanding. Like maybe it's enough for you to just work with synthetic data. And there are techniques to generate synthetic data based on real data. Like in a hospital, they have their actual patient data. There are techniques to generate synthetic data based on that real data, and then the synthetic data is sufficiently anonymous and can be released for research purposes. Yeah? That may be enough for you. Maybe you want to use a technique called differential privacy, right? Which is sort of similar, where you also have the original data, but it's distorted by adding some noise to it. And then you get a new version of the data set that sufficiently protects the original data. But these techniques like synthetic data, differential privacy, it's not may cause accuracy loss, they do cause accuracy loss, which in some settings may be problematic. Yeah? If you want to protect privacy while respecting accuracy, then you would need to use techniques from cryptography. So then you would study that. Yeah? So I think to answer that question in a nutshell, you would need to first figure out what your needs are. Is it important for you to have high accuracy, even though the computational cost will go up and you will need to use some techniques from cryptography, which will make it more challenging, right? Or can you get by with using data that has been anonymized by adding noise using differential privacy, for instance? Yeah. And there are some libraries out there, and like it's still kind of in an initial phase, but more and more libraries are coming. So a nice one to use if you are, for instance, familiar with PyTorch and you want to do some secure multi-party computation in combination with that, you can use Crypton, Facebook's library. For differential privacy, IBM is developing a library, so you can look around and you can see what the different companies are providing. But the first thing would be, what is important for me in terms of full privacy protection, wanting to preserve accuracy, right? And then if it's a yes for I want to fully protect privacy, I want to fully protect accuracy, then it's going to be cryptography. Yeah. If you're willing to make some sacrifices when it comes to accuracy, maybe you can work with synthetic data.
Thank you for the answer. This is so helpful. And honestly, it's an exciting field, I think, to see what's going to be developed in the future, because it sounds like a lot of things are just beginning to take off. We have one final question. This one's about the cloud deployment specifically that you were using. The question is, the multi-server decomposition implies that network speed is a bottleneck. Is this accurate? And if so, do you look at Azure network speedup services to address this problem?
It's not a bottleneck. No, the network speed is not a bottleneck. What is a bottleneck is that the servers each locally have to do some computations, and then they have to wait for each other. So it's not like a distributed system where a lot of computations can happen in parallel. We try to parallelize as much as we can, of course, right? But the communication is not like the network bandwidth is not really the bottleneck. No.
Cool. That's an interesting point to keep in mind. Sorry, CPU bound, it sounds like. Okay, well, thank you for your time, Martine, and for sharing with us such a great overview of all of these techniques and technologies.
Thank you.
Cool. I think we can stop recording now.